Hi guys, this is the pericyclic reaction and it is of part 2 and part 1 I have already discussed. So if you don't watch the part 1 of pericyclic reaction where I have discussed some basic concepts on pericyclic reaction, then please watch this video and then come here, otherwise you cannot understand whatever I am going to say in this part 2 video. Okay, in my earlier video I have told you that how to draw pi molecular orbital picture of some acyclic molecule like 1,3-butadiene and ethylene, and there I have told you that a system like 1,3-butadiene where there is 4 carbon atoms, and that is why there is 4 p orbital, and pericyclic reaction is completely a game of p orbitals. So as there is 4 p orbitals, so we will first draw the 4 p orbitals of 4 carbon atoms and 4 level of energy, and we will put nodes one by one to each level with higher energy. And for example, psi 1, this is the lowest energy level, that is why there is no node. For psi 2 there is one node, as 2 minus 1 is equal to 1, and as it's maintain the n minus 1 rule principle, for psi 3 there is 2 node, as 3 minus 1 is equal to 2, and for psi 4 there is 3 nodes because 4 minus 1 is equal to 3. So I have told you that the nodes will be of same distance from the center. That is why we will put the nodes in this fashion. So I have also told you that in ground state what is the electronic configuration of this molecule, and what is HOMO, that is highest occupied molecular orbital, what is LUMO, lowest occupied molecular orbital, what is SOMO 1 and SOMO 2, how it generates in excited state or photochemical condition, and then how its electronic configuration, what is non-bonding and zero level energy. This is, you can see, this is the energy diagram, below which the energy decreases and above which the energy increases, and below the line all the molecular orbital is bonding molecular orbitals, and above the line all the molecular orbitals is antibonding molecular orbitals. And in this line, if there exists any molecular orbital, it will be non-bonding molecular orbital. Okay, I have also told you in my earlier video that I will, in the next video, I will tell pi molecular orbital picture of a cyclic molecule like benzene and others. So definitely we will learn pi molecular orbital picture of benzene. Listen carefully. Pi molecular orbital picture of cyclic molecule is not similar to the pi molecular orbital picture of the acyclic molecule. This molecular orbital do not follow the n-1 rule. It follow another rule, that is, you can say we can derive this pi molecular orbital picture from Frost cycle. Remember Frost cycle. So how to draw Frost cycle? The process is, firstly you have to draw a circle, and in this circle you have to put the shape of the molecule of which pi molecular orbital picture you want to get. For example, here I am going to derive the pi or molecular orbital picture of benzene. That is why I will put the shape of benzene in this circle, and the shape will be in the way that one particle will be of downwards. So that's how I draw the shape of benzene inside this circle. So now you are observing that the 6 vertices of benzene ring touches the 6 particular point of circle, and in this particular point I will draw a horizontal line in that way, and also I will draw a dash horizontal line along the center of the circle and the molecule. These 6 horizontal line is the position where we will draw the pi MOs of benzene. So there are definitely 4 energy levels. As the energy increasing in this way, This horizontal diameter will be called your non-bonding or zero level energy, and above which there will be anti-bonding molecular orbital, and below which there will be non-bonding molecular orbital. And definitely if there exists any horizontal line along this dashed horizontal line, then it will be called non-bonding molecular orbital. Okay, so uh, and in my left hand side I have drawn this pi emos of benzene. This is similar to this 6 horizontal line, and now for benzene this will be psi 1, and this will be psi 2, psi 3, psi 4, psi 5, and this will be psi 6. Remember, psi 2 and psi 3 is at same energy level, that is why they are degenerate. Same are of same energy. Okay, so for psi 1 or the first energy level, there is no node. That is why we will simply draw this pi emos where all the p orbital have same symmetry. For the second level, where psi 2 and psi 3 present, actually there will be only one node, but it is impossible to draw a node for a cyclic system. That is why we will draw nodal plane instead of node. So we can draw a node in psi 2 and psi 3 along this line. Okay, now the pi orbital will be in this way. Okay, I hope guys you understand. So why I just erase these two p orbitals? Because earlier I have told you what is nodal plane. Along the nodal planes there is least tendency of getting electron. That is why I have erased these two p orbitals, as the nodal plane of psi 3 is along these two p orbitals, and following the definition of nodal plane, there will be no electron density. Now your psi, for the next energy level, psi 4 and psi 5, there will be two nodal plane, and the two nodal plane can be drawn in this fashion. Now for the next energy level, where psi 6 exists, there will be three nodal planes, and we can draw the nodal plane in this way. Now the pi mo will be where all symmetry of all the p orbitals will be alternates. Now the pi molecular orbital diagram for benzene. Earlier I have told you how psi 1, psi 2, psi 3, psi 4, psi 5 and psi 6 exist, and where the horizontal line present. So this is simple like that. And as we know that in benzene there is 3 pi bonds, that is why there is 6 pi electrons. So we can simply put the electrons in this way. Okay, so whatever feature exists in Frost cycle I have just told you. If you don't follow this, please rewind this video and then understand it. So we can also determine the aromaticity of molecule through Frost cycle. The molecule is aromatic only if all the bonding molecular orbital below the central dashed line is contains 2 electrons. So here all the bonding emos contain 2 electrons. That is why benzene is aromatic. We will also see some other molecules where this aromaticity do not exist. Now learn the pi molecular orbital diagram of cyclobutadiene system. So we know that cyclobutadiene has two pi bonds, and it has 4 carbon. That is why 4 p orbitals exist. Similarly, as this is a cyclic compound, we have to follow the rule of Frost cycle. Inside it, draw the shape of cyclobutadiene or a rectangle in this way with one vertex pointing downwards. And if we draw the horizontal dashed line, as there is psi 1, there is psi 2, there is psi 3, and there is psi 4. This horizontal line cuts through 2 pi MO energy level of cyclobutadiene, that is psi 2 and psi 3. So here I have already drawn pi MO of cyclobutadiene. So for psi 1, as there is no node, we will draw the pi MO simply. For psi 2 and psi 3, there will be one node, and we can draw the node in this way. So just simply draw it. Sorry for saying each time that it is node. Actually, it is nodal plane. Always remember, if I say the same thing while teaching you, but always think this is nodal plane. This is not node. Okay. Then for psi 3, for psi 4, there is two nodal plane, and this will be in this manner, where all the p orbital, symmetry of p orbitals alternates. That is how we can draw the psi 4. But if you observe the first cycle, we will also found that this horizontal line that denotes this non-bonding energy level or zero level energy level is along psi 2 and psi 3. It means that psi 2 and psi 3 are non-bonding molecular orbitals, while psi 1 is bonding molecular orbital and psi 4 is anti-bonding molecular orbital. So cyclobutadiene has 2 pi bonds, that is why it has 4 pi electrons, and we following rules of LCO, linear combination atomic orbital, we draw the molecular orbital diagram of cyclobutadiene. Remember, cyclobutadiene has 4 pi electronic system. Okay, that is why it is anti-aromatic. But you can also say from this Frost cycle that it is anti-aromatic, because earlier I have told you that the molecule will be anti-aromatic only if all the bonding MO below the central dashed line contains 2 electrons. But if all the MO above or on the horizontal line contains any electron, then it will be anti-aromatic. That is why cyclobutadiene is anti-aromatic. Next, come to your cyclopentadienyl system. So again, if we draw the Frost cycle, here this horizontal dashed line will pass through here. Similarly, we get psi 1, psi 2, psi 3, psi 4 and psi 5. So for psi 1 there is no node, for psi 2 and psi 3 there is one node, and for psi 3 and psi 4 there is 2 nodal plane. We can simply draw it in this way. Okay guys, I hope you understand. And cyclopentadiene has 2 pi bonds, that is why it has 4 pi electrons, and we can simply draw this out. So can you find that cyclopentadiene is an anti-aromatic system, because here psi 2 and psi 3 below this horizontal dashed line contain only one electron. If we add one more electron to psi 2, it will become cyclopentadienyl free radical. Okay, and if we add one electron again in Psi3, it will become cyclopentadienyl anion, where you can see that all the bonding MOs below this horizontal line have 2 electrons. That is why we can conclude that cyclopentadienyl anion is aromatic, while this free radical is anti-aromatic, and this one is also anti-aromatic. So I hope guys you understand all the things I have discussed here. If you have any doubts, you may definitely ask in the comment section. I will clear those doubts. Please respond. Otherwise, I cannot understand what is your problem, where you are getting confused. Okay, so please keep commenting. In the next video, we will learn electrocyclic reaction and then cycloaddition and sigmatropic rearrangement one by one. So I hope guys you like this video, and if you have any doubt, please comment, and don't forget to share and subscribe to my YouTube channel. Thank you for watching.